Okay, hey, welcome to another exciting episode of Advanced Level Chemistry here at Spain Park. Today is Wednesday, 9:23, 9:24. What is it? 9:24. Time is just slipping into the future. Yeah, because we're having so much fun. That's exactly right. All right, so Fallon, I need you to come up here, and I need you to look inside this white tub and tell me what that water looks like. Say that again for everybody in the world to hear.
Gross.
It looks gross, okay? It's nasty because there's just been junk. It's been tap water put in here. There's dirt. It's just nasty water. So we're going to go through. Okay, thank you very much. You did a great job. Okay? So now when we go and we turn this on, did the light come on? It's not plugged in. Okay? What are we going to, oh man, is this really, it sparked on me. I think I might have blown that fuse. Okay? Now it is on. The fan is blowing. So what's going to happen here? It's going to, how is it purifying the water? What's the process called? Well, it's evaporating the water, but the whole process is called distillation. Distillation, okay? Now, how is that? So we can do the same thing. We can kind of visualize it over here a little bit easier. Turn this on. Turn this on. Turn this on. Okay? So now we have a flame, so I'm going to heat this up. So here's my nasty water here. And I turn this water on. So what's going to happen here? So what's going to happen to this water is I'm heating it up, obviously. It's going to evaporate. It's going to boil, turn into steam, and then the steam comes here. Now, why am I running cold water? What did you say? Make it condense. So the steam is going here, but all of the junk that's in here, the salt, the dirt, the stuff that's in the tap water, all of those things have a much higher boiling point than water. Salt is a solid at room temperature. You got to get salt super hot just to melt it, even super hotter, that's such a thing, super hotter to make it boil. So when this water is boiling at 100 degrees, the salt's not going to boil. So where's the salt going to stay? In the bottom. All the junk, all the dirt has a high boiling point, so it's all going to stay in the flask. Okay? Oh, you see the water splashing up? Yeah. So as this heats up, the steam comes over here, so this is my distilled water. Remember I said a solute and a solvent can be separated. We have a mixture right here, and it can be separated by physical means, simply heating it up and evaporating, boiling the water off, and leaving the junk behind. That's a physical means of separating. Okay? So this is so we can kind of see it. This is the laboratory setup for a distillation. That is the commercial way. So anytime we need to do a lab with distilled water, most of the time we just go to Walmart and buy a jug of it for $1. Okay? But distilled, somewhere in the distilling company, they've gone through and they've heated the water up and then collected the steam and collected it, condensed it, collected it, and that's your distilled water. Okay? So we can kind of see this as it's heating up. You can already start seeing the steam, but it's hitting the glass here that's already cool, and so it's condensing here, and it's not making its way down. So as we continue to heat it up, it's going to go there. Now, we had the 4 ways of separating. The first one was filtration. That's your red solid. Remember the red solid we did yesterday in class? Okay? Why didn't it go through the filter paper? It was too big. So what type of mixture was it? A suspension. But I put in extra amounts. I only put in a little bit of the silver nitrate. I had extra amounts of the yellow, so not all of the yellow reacted, so it's still a solution. So what did it do? Did it get stopped by the filter paper? Why not? The solute particles are too small For solution, they go through the filter paper. Only a suspension, the particles are big enough to where they're going to settle out due to gravity and be collected by filtration. Okay, how did we know that a solid was formed? What happened to the color or the transparency of the solution when? So what? Okay, how did I know that, when I mixed the two together, how did you know something happened? Turned a different color and got cloudy. That's what I'm trying to say, is that this is really our suspensions here. And we're at the very end of the day. In a suspension, all are cloudy. A solution is always going to be clear. Not necessarily colorless, but clear. Suspension is going to be cloudy. That's going to be you got something big formed in there when it got cloudy. So if you have a colloid that's cloudy, that means that you're on the high end, the big end of the medium. Your medium is kind of right in the middle. The low end of medium is going to be clear. The big end of medium is going to be cloudy. The small end of medium for a colloid is going to be homogeneous. The big end of a colloid is going to be heterogeneous. All right? So now you can start seeing, so the water is beginning to boil here. So now that steam is going to hopefully start coming across, and we'll begin to see some condensation occurring. Let's see if we can see actually anything dripping down into here. The same thing's going to be happening over there eventually. Watching water boil, how exciting. So we have, how does the centrifuge, while this is going, how does the centrifuge work? It spins it, and what goes to the outside? The heavier particles. And we're going to study that more when we get into nuclear chemistry. We're going to see that. I don't know if you guys follow the news at all, but you know that Israel and Iran were in a war, right? You know that much. And you know that the United States went in and helped Israel a little bit, and we bombed that one bunker with our big bomb, and that in that bunker, Iran had a bunch of centrifuges, and those are used to separate uranium-235 from uranium-238. So which one do you think is heavier, 235 or 238? Ooh, it's going a little bit too strong now. Okay? So it's about to blow the top off of here. But now the steam is forming and coming down, and at some point we should see a drip, a drop, or whatever, if it's working right. But we'll just turn the heat down, have a mild heat. Okay? So we blew up the centrifuges that Iran was using to separate the 235 from the 238, because the 235 is what makes atomic bombs. And so they needed more of the 235 and kind of separating it out. So the reason why we're going to study nuclear chemistry is because there's so much of that stuff going on in the world. We need to be wise. We need to be educated as far as what the dangers are, what's really going on. And so when they say stuff on the news, we're educated about it. Okay? So I'm hoping to see a drop of water come by. It seems like something's forming right there, but we'll see. We'll just let that keep going. All right, so we have our four just main types of ways to separate. We were doing that at the end of class yesterday, so I want to make sure that we know that. So we have filtration. We separate based on the size of the solute particles. Okay? Separation, centrifuge, we separate based again by the mass. The heavier ones go to the outside. Distillation, what's the property that we use to separate? The boiling points. So you make sure you put that, maybe if that's not in your notes, it separates due to differences in boiling points. Okay, okay, so that's distillation, okay, is a means of separating a mixture based upon differences in boiling points. Again, if you've ever heard of moonshine, go up into Tennessee in the woods, they're making alcohol, they use corn, they use yeast, and they have, they put different kinds of flavors, apples or different things in there for flavoring, and it's all in this big pot. It's a mess, but the alcohol gets made, and then they have to distill it. They have a still out in the woods, hiding from the cops. And so they're basically going to heat this up. Now, alcohol boils at 80 degrees. Water's at 100. So they're going to control the temperature, 80 degrees, boil it off, and then a lot of times they just have a metal coil that's air cooled instead of water cooled, and then they recondense and they distill, leaves all the junk behind, and they just collect the alcohol over here in the jug, and they sell that as moonshine. Okay, and apparently it tastes pretty strong. I've never tasted moonshine. I've never had a desire to taste moonshine, but apparently it's like pure alcohol. It's a pretty strong flavor. Okay. Now the fourth one that we're dealing with is called chromatography, and I think you guys did this in biology, but we're going to watch just a little 1.5 minute video, just seeing paper chromatography and just kind of seeing how that works. Okay, paper chromatography.
This video shows an example of a chromatography experiment. The goal of the experiment is to separate the different pigments of ink which are present in a wet erase marker, which we'll see right here. So this the marker is wet erase, which means that the pigments are water soluble. We'll start our experiment by drawing a line with the marker on the chromatography paper. Then what we want to do is insert that chromatography paper.
So did you guys do this in biology?
With water in it. We can see that the water will start to rise up the chromatography paper because of capillary action. You'll note this happening very quickly because this is 16 times speed playback. We can see that the ink, which originally was black, is starting to separate into different colors. This is because the different pigments have different properties. Some of them are...
Okay, so this is really all I wanted you to see. So notice that it's separating. This is water, and as the water rises up the filter paper, and you know that if you put paper in water, it just naturally gets wet. Capillary action makes it work its way up. Okay, it's separating it into the colors. So it's separating all of these colors were in the marker that was down here at the bottom. It's separating the mixture of colors that was in there. And the big difference is that it's separating based upon the solubility of the colors in the ink, or the solute in the water. The blue, this blue purplish color, was the most soluble in the water. And so therefore it followed the water up the highest. The yellow was the least soluble in the water. Now, you guys know that if you have two different types of paints, right? You have a water-based paint and you have an oil-based paint. You know, like if you have a spray paint, or if you ever did an oil-based art picture. Oil-based stuff, you have to use turpentine or mineral spirits to kind of clean up. You can't clean it up with water. You guys know what I'm talking about, that there's two different types of paint. You've all done some little craft, something where you've used an acrylic paint that you have to use turpentine or mineral spirits to clean. If we put something like that down in here, mineral spirits down here, it's probably going to be reversed in terms of the color. That the yellow would probably be more soluble in the turpentine, and the blue would be the least soluble in it. And so the colors get separated based upon the solubility in the solvent, whatever's rising up the paper. So you can tell the difference in the solubilities there, and we can learn more about that when we get into bonding and we understand more about the properties of the substance. But the thing I want you to know is chromatography is a way of separating mixtures based upon their solubilities in the solvent. So distillation is based upon boiling points. Filtration is based upon differences in the size of the solute particles. Chromatography is based upon differences in their solubilities in the solvent, whatever's going up the paper. All right. So today, we want to go to our second class of matter, which are going to be elements. Now, if you look at your periodic table that I gave to you, okay, you will see there are 180 on the phone. There are 118 known elements. Okay? I do want you to come over here. Back in 2000, when this was printed, there are still some gaps, but now it's pretty much been all filled in until 118. And they all pretty much have names now, and whoever discovers them makes them. Now notice that these are outlined, okay? That means that they're man-made. They make them by smashing nuclei together, and if they can do it just right, the nuclei will fuse together and you get a bigger nucleus with more protons, and so you can make an element. And if you make it, you get to name it. And so they've gone through this, but only up to 92 are what we call natural elements. So there's 118 known elements, but there's only the first 92 are known as natural elements or pre-atomic age. The atomic age started with the advent of the atomic bomb. The whole Manhattan Project, that all entered into the atomic age. Okay? So in the 50s, many of these were all made. All this new technology, ooh, we can split the atom, we can do all this with the atom, all this knowledge was coming out. Most of these elements were all made, these first ones were made in the 50s and 60s. Okay? So, but only 92. The reality is it's only 90 because 61 and 43 do not exist anywhere on Earth. You can't go and dig up anywhere. You can't dig up a 61 or a 43. Technetium was the first man-made element. Okay? It still doesn't exist anywhere, but they have found some promethium out in stars somewhere, and we'll talk about in chapter 4 how we find that.
Wait, how's it an element that doesn't exist?
Because they can make it, because they can smash nuclei together and make one that has 61 protons in it. It just doesn't exist naturally. It does exist. Now they do believe that this exists naturally in stars, in some distant stars, and we'll talk about how they figure that out later, but they have a way of knowing what elements are in stars. But so on Earth, if you're going to go dig up something, you're only going to be able to dig up 90 of them. Okay? There's none of these you're going to find in nature, and these two you're not going to find in nature. Okay, so there's only really 90, there's 92. But what's the smallest part of an element that can maintain the properties of that element? What's the smallest thing of gold that can still be gold? An atom. Okay? An atom is the smallest part of an element. Now, most elements can exist as single atoms. You can have a single atom of gold, a single atom of copper, a single atom of, aluminum. But there are 7 what we call diatomic elements. What does diatomic mean?
2 atoms.
2 atoms. Everybody take a big breath. What are we breathing in? What do we need to live? Oxygen. But is it just O?
No.
It's O2. It's O2. It's a diatomic molecule. It's going to float around as a diatomic molecule. Now, when we get into bonding, we'll learn why it's more stable to be O2 than just O. But O2 is going to be there. What else what did we say was another component of air?
Nitrogen.
Nitrogen. So what's it going to be? What form? It's gas, but it too is one of our 7 diatomic elements. We're breathing in N2. You're not breathing in just nitrogen, you're breathing in N2. Now it doesn't do anything. You breathe it in, breathe it out, breathe it in, breathe it out. It doesn't react in your body at all, it's just there. Now it's good that it's there because if things were pure oxygen, everything would burn super fast and we'd probably age super fast, and nitrogen does things to slow everything down, but it doesn't really do anything. It's just splashing everywhere. I was wondering, I feel like it was getting wet. This whole floor is soaking wet. I'm got to wipe out. Okay, we're gonna turn this off. Whew. You're just sitting there watching it splash. Okay, gonna wipe out. There's a lot. Okay. The way you can know these is it starts at 7 and makes a 7. There are 7 diatomic elements, things that exist as a diatomic molecule. nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Hydrogen gets, acetine's radioactive, so we kind of ostracize it from the family, and we substituted hydrogen. Another way to think about it is anything that ends in gen or ene, G-E-N or I-N-E. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Acetine, again, is radioactive, so we just kind of don't mess with it. Okay, I'm not sure if it would be diatomic in its natural state or not. It probably would be. Okay? Now, whoop. Squeaky, squeaky. Okay, I'm telling you, there's a ton of water here. I didn't realize I was making such a mess. Now, y'all, by the way, you need to highlight these. You need to know these 7. Okay? You're going to be responsible to know these 7.
It was just in the 7 on the.
Just those 7. Okay? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, but then hydrogen comes added in as the 7th one. Okay? They're always, so when you have pure oxygen, and we're going to need to know this because when we're doing a chemical equation, whenever we're doing a reaction, if we're dealing with oxygen, it's going to be O2, not just O. Gold is just going to be AU. Copper is just going to be Cu. But oxygen is going to be O2. Nitrogen is always going to be N2. Now that doesn't mean when it's in a compound it has to be that, because we have H2O. It's only one oxygen. It's just when we're pure oxygen, pure nitrogen, pure chlorine, it's always going to be diatomic. Now there are other molecules, other elements that are polyatomic molecules. Okay? If I look at this sulfur right here, this sulfur, if we could look at it on a very small microscopic, get into an electron microscope, get down and see it, we'll see that the sulfur is actually in an 8-membered ring, like the shape of a rhombus, a 3-dimensional rhombus. This 8-membered ring, and then those rings stick together to make the solid. So there's this S8 in here. That's the natural form of sulfur. Okay? So it's not individual atoms that are all stuck together. It's 8-membered rings of sulfur that are all stuck together. Now phosphorus, P4, is kind of crazy. P4, have y'all ever played, I'll just stay back here, this is on video. Have you ever played with Tinker Toys or something and you're trying to make a shape and you put the sticks together, but you're really kind of forcing it to be together, and so anything you touch, it breaks back apart, okay? That's the way P4 is. It's in a square, but it doesn't really want to be in a square. The angles are not right. So it's very unstable. Matter of fact, it's so unstable that if you expose it just to air, it reacts with the oxygen in the air, and it's called an incendiary device, and it just bursts into flames. Okay? I used to do a cool demo, but they don't let me do it anymore because different schools, people, one teacher sent this whole class to the hospital. Others have caught things on fire that catch on fire, so they don't let us have this in schools anymore. But you can take P4, white phosphorus, you have to store it under water under normal circumstances because it'll just react with air and catch on fire. So you store it underwater, but I took some, you take it and you break it up into small pieces, and I dissolved it into what's called carbon disulfide, CS2. It's a kind of like, it's a real oil-based, but it evaporates super quickly. So I would make this mixture, the phosphorus would dissolve in it, squirt some onto a piece of filter paper, just like this, and then put it on a graduated cylinder. The carbon disulfide evaporates quickly, leaves a white powder of white phosphorus that then reacts spontaneously, just all on its own with the air, bursts into flames, and makes a whoop sound as the heat goes down into the graduated cylinder. It's called the barking dog demo. Okay, and the filter paper goes up in fire all on its own. It's really kind of cool. Okay, I would love to see that. Okay, you might be able to look it up on YouTube. I should probably look it up and just see. Well, let me just see. I didn't do this in the other class, but let's just see what I can find. I don't know. I'd be careful what I'm looking for here. I'm going to do this on video. let's see this. Let's see if this is it. Let's see how this goes.
Well, I just want to do a short little demo for you. It's what we fondly call the barking dogs. I'm going to take a little bit of this solution and set it up on top of filter paper on top of these graduated cylinders. This solution contains some P4, which is solid phosphorus, and it's not necessarily dissolved. It's as though it's suspended. It's just covered with some carbon disulfide, and the carbon disulfide is going to evaporate away and expose the phosphorus to the air. And phosphorus is extremely reactive in the presence of oxygen. So we have a little bit of solution on top of the phosphorus, and that's evaporating away, and when the oxygen in the atmosphere gets a hold of the phosphorus, we'll have a nice reaction on each of these graduated cylinders, and it's going to take a few seconds for the evaporation to occur. We call this the barking dogs for a couple of reasons. I get a hold of this in a couple of seconds here. Sound like a dog?
Okay.
Is that funny? We waited a
There you go.
long-
I used to be able to do that. I used to be able to do that one in class, but we can't do it anymore. Okay.
Why did the one on the left fill up with so much smoke than the other one?
I guess just because it looked more, because it's smaller, so it looked like more, or the fact that it was bigger, the smoke was able to escape, not go down. I don't know. Maybe as the amount of phosphorus that was actually on it. That's kind of, but, okay, so we find that phosphorus, come on back, okay? We find that phosphorus, does that. That's kind of a cool little fun demo. That's nice. But some sadistic person said, "Hey, let's put this into a hand grenade or a bomb." And in Vietnam, actually in the Korean War, and then in Vietnam War, they would have phosphorus grenades, and they would throw the grenade, and it exploded. It would send white phosphorus out. Anything that it embedded upon would catch on fire, including people. And so, if it got embedded in you, it would just begin burning, and with the there, you would just basically be burning all over. Have any of y'all ever heard of or seen the show, TV show MASH? It's a very old TV show, but MASH stands for Mobile Army Surgical Hospital. And this was about doctors in the Korean War, and somehow or other they made a comedy, a sitcom out of a MASH unit in Korean War. But one of the episodes, one of the soldiers had gotten hit, and they were all surgeons. The actors were all surgeons. But one of the soldiers had gotten hit with a phosphorus grenade, and they had to take him and put him in a cow trough full of water, get him underwater to stop the reaction. Because as long as he's exposed to air, he would just continue. His skin was burning, and he was just in misery. So they had to put him under in a cow trough underwater, and then surgically take out the phosphorus out of the skin. And I'm sure that actually happened in Vietnam, because in the 80s, a youth pastor was traveling around, and he had gotten hit by a phosphorus grenade in Vietnam, and his whole side of his face and all down this side of his body was all just burned. You can kind of tell the burned scars, and but he was telling kind of what happened and how he had gotten through it. And so it's just very, very nasty. And so they not only did that, they had bombs that would go, and then it would just catch anything that it embedded upon, indiscriminate of whatever it hit, it would just catch it on fire. It's called an incendiary device. So that white phosphorus. Now, a different form of phosphorus, P8, is what we call red phosphorus. Have any of y'all seen a Strike Anywhere match? Now, red phosphorus is a little more stable than white phosphorus. Red phosphorus won't burst into flame, just exposed to the oxygen. But a little bit of friction, strike it anywhere, get a little bit of friction, it'll catch on fire. So they're using the red phosphorus for something good, a Strike Anywhere match. Okay, and that's kind of the thing we talked about, pure science versus applied science. Are we going to use it for good? Or are we going to use it to burn the crud out of people, in a war? How are we going to use the technology that we know? So I say all of that that some molecules exist in their natural form, some elements exist in their natural form as polyatomic molecules. Now, you must know these, you don't have to know those. Okay? You are responsible to know these 7. But you don't have to know these. This is just for me, just giving you a little bit more to the story. Okay? Now, what do we know about symbols? Chemical symbols describe elements. Okay? What do we know always about the first letter? Always capitalized. What about the second letter? Always lowercase. What if there happened to be a third one? It's going to be lowercase as well. Okay? Now, these here in the old days, before they were all named officially, they just, I love this one, the 111. They use the Latin name for 111, the unium. Okay? It's just, that's Latin for 111. It's just a bunch of unis. Okay? So these are all the Latin names, but now I think on your periodic table, they're all pretty much named. So let's talk about the names of the elements. The first 70 were just kind of always, but some of them were described by their characteristics. First off, you just have the phonetic sounding: hydrogen, helium, lithium, beryllium, Be, boron, carbon, nitrogen, carbon, what was I can't believe, nitrogen, oxygen, fluorine, neon. But then you get to sodium, Na. Where does that come from? Na. What you think? Obviously, maybe different language. Okay, it comes from the Latin natrium. It's the Latin name for sodium. And then you get magnesium, aluminum, silicon, phosphorus, sulfur, and then chlorine. Chlorine has been around forever. Now, it was, by the way, it was the first war gas used in World War I by the Germans, and it was called mustard gas. And chloros is the Greek word meaning greenish yellow, because it's a greenish yellow gas. Because it's kind of got a yellow tint to it, they called it mustard gas in World War I. And it actually forms hydrochloric acid in your lungs and just kind of causes you to choke and gag and die if you breathe it in. That's why if you ever see the war movies of World War I, they always had the gas mask on in the trenches, because they were bombing with chlorine gas, just trying to maim as many British and American soldiers as possible. I mean, it's a nasty gas. And then argon, and then potassium comes from catrium, which is kind of Latin for potash, because there's a lot of potassium in ashes. Some of where they were discovered, copper is cuprum, was the name of an island where it was discovered. Arsenic, they believed that metals had sexes, and that they had female and male, and arsenic is poisonous, and they had something about its gender in that. Bromine comes from the Greek word meaning bromos, meaning stench, because it's got a real nasty stench smell to it. So a lot of the names of the elements are come from descriptive. Gold is from the Latin aurum, A-U-R-U-M, meaning shining down or shining one, because it's got the shiny metal. And a lot of times they would just have idols made out of gold, and they thought gold was really kind of supernatural. Okay? Then we come down here, okay? And then when you start making these, and so obviously thorium is named after Greek god Thor. Okay? I have no idea what protactinium is named after. Maybe a geometry person with a protractor or something. I have no idea on that one. And then this one's named after the favorite planet of everybody that nobody likes to say, the planet Uranus. Okay? So it's uranium. Okay? I always think about this when I was a very young teacher in my 20s. I was going through and doing this, and I had a student that was all into the planets and all that, and he very, very sincerely just asked me a question. He goes, "Mr. Hobbs, why is Uranus green?" And I just responded to Teddy, "That's kind of a personal problem. I'd really not rather answer it." And I kind of embarrassed him. I felt bad ever since on all of that. But I mean, there's all kinds of jokes about the planet. And even in the 70s, they sent a spaceship, a satellite, Voyager, an unmanned ship, to go to all the planets and take pictures. And when it finally got to the planet Uranus, the little newscaster ladies would have to say, "Oh, we now have some pictures of the Voyager flying out around Uranus." And it just, of course, then all the jokes, would come from that one as well. And so they really need to now. So they tried to rename it Uranus, say to repronounce it, but that doesn't sound any better. Uranus. I mean, you can't win for this. They just need to change the name of that planet. Apparently, is there a Greek god that's named after somewhere?
No, it's the only planet known as a Roman god.
That is the only one? Okay. But then we have Neptunium, and then Plutonium. Is it a planet, not a planet? Is it a planet, not a planet? Okay. Is it a dwarf planet now, whatever that just means? Okay. Now, in the 50s, listen, in the 50s, many of these compounds were made by bombarding the nuclei together at Lawrence Laboratories in Berkeley, California. So we have americium, America, curium, named after Marie Curie, but then you have berkelium, californium, then over here is lawrencium, okay, just named after themselves. Then we got einsteinium. Fermium is named after Enrico Fermi, who was one of the Italian scientists who came up with the whole splitting of the atom and being able to do that first. Does anybody know Mendeleevium? What did Mendeleev do? No? That's Mendel. That's who did the, the whole biology stuff. He was the one that put the first periodic table together. Was Mendeleev. Okay? And then, do you guys know this, the Nobel story? Where the Nobel Peace Prize came from? He invented dynamite. And he invented dynamite with the intent, y'all listen, with the intent of, being able to use it for construction purposes and be able to build roads and, do all that. But then it was used to make bombs and destroy, buildings and kill people. And he was so distraught over the fact that his discovery was being used for killing of people and bombs that he took all of the money that he made from his discovery and developed the Nobel Peace Prize and tried to motivate anybody to promote peace rather than using his dynamite for destruction. That's where the Nobel Peace Prize came from. Okay, so he was a scientist that, again, so Nobelium was named after him. And then just a couple other stories. Glenn Seaborg was probably the most current scientist. He didn't die until the late 90s. He's responsible for all of these two rows of the periodic table being down here and why they're separated and grouped together. Okay? But they wanted to name element number 104 after him in the early 90s, but he was still alive, and the IUPAC, the International Union of Pure and Applied Chemists, aka the chemistry gods, they had this unwritten rule that, hey, you got to be dead before you can have something named after you. And so there was all kinds of battles and arguments and whatever, but the IUPAC wouldn't let it happen. So 104 was named after Rutherfordium, another famous scientist that you'll read about. And then is Ernest Rutherford. So then Seaborg died, and then so they named 106 after him as soon as he died. Lastly, for women's suffrage here, Lise Meitner. Lise Meitner lived in the 20s, and she was one of the premier people that learned that, hey, the atom can be split. And she was working with Otto Hahn and working together, but she was the brainchild behind it. But women were highly discriminated against back then. In Hidden Figures, where the ladies had to go across the street just to use the restroom, there was no restroom for a woman in the labs where she was working. She had to go across the street as well in order to just be able to use the restroom. She was highly discriminated against because women just weren't respected in the science world at that time. Well, she ended up, it was in Germany, and she is of Jewish descent, so she had to flee. But she was sending letters back and forth to Otto Hahn, and he ended up publishing all of that and taking all of the credit and ended up winning a Nobel Prize for all the work when she was actually the one that did almost everything. And she was the brainchild behind it. Then finally she got some recognition, and they named this element meitnerium after her. Okay? So a little women's suffrage there in the scientific world. All right. Real fast now, because I spent way too much time on that. Oh, wrong page. We want to go to the three classes. We have the three phases of matter. Now we're going to go to the three classes of elements. We have metals, nonmetals, and metalloids. So we can see metals, all elements to the left of the zigzag line. Where's the zigzag line, obviously? Now, do you know what the official name of that is? It's called the zigzag line. Okay? It's the zigzag line. So everything to the left of that. So which one do you have more of, metals or nonmetals? Where do these two rows fit? Okay, if you look, 57, 72, 89, 104, star, 2 stars, star, 2 stars. These all fit in right there. So what does that make them? Metals. They're called rare earth metals, intertransition metals, and we'll learn that in a little bit. Okay? So what are some of the properties of metals? How do I know? What this is? Okay. What's the first thing that stands out about this? Shiny. What's the fancy word for shiny? It's got a luster. That means shiny. Okay? We're so out of time. Okay? They're good conductors. Good conductors of heat and electricity. Which is why pots and pans are made out of metal. Which is why wire is made out of metal. Because they conduct heat and electricity. They reflect heat and light. Have you ever seen an old antique mirror? Anybody know? How can you tell if a mirror was old? It's got the glass in front. Almost all mirrors still have a glass in front. But have you ever seen an old mirror? What? But they got little brown spots. Have you ever seen that, like a little brown spot in the mirror?
On the side?
On the sides and stuff? Because mirrors, a good expensive mirror is actually a silver back. You polish the silver, and that's why good mirrors are very expensive, because it's actually a thin coat of silver, really polished. But the silver over time will tarnish, basically rust, react with the oxygen and the sulfur in the air and rust, and then little brown splotches are the glasses to keep the oxygen and the sulfur from getting to it, to protect it. But over time, the seal breaks and you get a little bit of stuff in there and it begins to tarnish. Okay? But metals, true mirrors reflect light. Most mirrors are made with a metal backing of some polished metal is what makes a good mirror. They reflect heat and light. Now the time's going to run out, but what does malleable mean? Bend or formed into shapes. What does ductile mean? So what? You're saying wire? Yes, can be drawn into wire. Okay? So, ductile, malleable can be formed into shapes. You guys can put up, but I'm still writing. I go to the bell. And this can be drawn into wire. You can go home and watch the video and fill it in. Good? Now, just real quick, we're not going to do them all, but what do you think non-metal is going to be? The opposite. They're not shiny. What's the opposite of a good conductor? An insulator. Okay? They don't reflect heat and light. And instead of being able to pound them into shapes, you hit them, they break into smaller pieces, so they're going to be brittle. Okay? So it's pretty much the opposite. And then metalloids are going to be those things that are just kind of right along the zigzag line. Properties of both. All right. So you guys have a good day, and go Jags.